Good morning, folks. A bit of another lengthy video here today. We have a number of examples to go over because the material that we're handling today has a lot of implications, and we can it will give us the skills to be able to handle a number of different kinds of polynomials and to be able to analyze them more thoroughly than we have before. Today's lesson, although it says 3.2 at the top, it is 3.3. And it's polynomial functions in factored form. That's what we're looking at right here. All right, now you have seen factored form before. In particular, in grade 10, you went over factored form. You went over quadratics, right? You went over factored form of a quadratic, and it looked something like this, where f at x was equal to a, which was a stretch factor, times x minus s, which was one factor, and x minus r, which is another factor. In this case, this quadratic would have two roots. One of them is at x equals s, and the other is at x equals r. Remember, a root or a zero or a solution or an x-intercept is where your function is crossing the x-axis, right? So we can see here this function, has two zeros. I'm not allowed to zoom in any further. It has two zeros, one at x equals s and the other at x equals r. Now, we know now that a quadratic is a 2-degree polynomial. That is, it's a polynomial with degree 2. We should be comfortable with that from our work in section 3.2 in the last video. If you're a little confused there, then head back a video. We can also express certain polynomials, not all polynomials, and we'll kind of get there, in factored form, where each factor will correspond to a zero. So again, in this case up here, we had two factors. One was x equals s, the other was x equals r. Or sorry, x minus s, the other was x minus r. These are factors. A factor is something that multiplies times an entire something else, right? So here we have two factors. Well, we can take this pattern and use it forward in with other polynomials, not just 2-degree polynomials, to come up with other factors of them. So let's say a function has a root at x equals 2. Then that is like saying our function will equal 0 if x equals 2. And that means we could rearrange x equals 2 to isolate for an x. That means x minus 2 equals 0. That could set our function to 0. So x minus 2 is a factor. Okay, so let's use that same logic for the next one. Well, then if a function has a root at x equals -1, then that means the function equals 0 if x equals -1. And we can rearrange this. That means x plus 1 equals 0. That's a factor. Okay, x plus 1. Sorry, you may be able to hear Sadie the puppy in the background barking here. And lastly, if a function has a root at x equals 5 over 2, where all of a sudden we're handling a fraction involved, then we have a factor. Okay, so that means that if x equals 5 over 2, then our function equals 0. We can rearrange this. That means 2x equals 5, and that is 2x minus 5 equals 0. So 2x minus 5, that's a factor that we're working with. Okay, now let's consider if a cubic function has three factors. Okay, so one of them is at x equals 2. One of them is at x equals -5. One of them is at x equals 9 over 4. How many possible equations can satisfy this description? Well, what we're working with here, we're working with f at x, and we know it has three factors, right? So one of those factors, this is, and I'm not going to go through this entire process every time. I just wanted to show you how we handle that. So that means our first factor is x minus 2. It means our second factor is x plus 5. And our third factor here is 4x minus 9. Okay, so we have all of those factors we're working with here. X minus 2. X plus 5. Mr. Saka did not plan ahead right here, but we're doing it using software that allows us to move it around. Times 4x minus 9. Okay, so these are our three factors. Now, is this the only equation that has these as factors? Pause, think about it. Can you think of another equation that has these factors? Absolutely. In fact, can we think of another equation, though, that's cubic that has these factors? Absolutely as well. We can just work with different stretch factors here, right? We could have the number 2 in front, or we could have a -3 in front. We could put whichever kind of stretch factor we wanted to here, and it would share these same factors, right? So we're just going to give it an A. Okay, so we can have an infinite number of different functions here that share these same roots that are cubic functions. Really, this should say it has 3 roots at x equals 2, x equals -5, and x equals 9/4. Now, in general, we call this a family of functions. Okay, so we can describe a family of functions with an a value, with an a term involved. So a family of functions has the same factors to the same exponents. So you'll notice the exponent on each of these factors was 1. Right? I could not have made any exponent anything else because it's a cubic function. Now we went over a little bit how to come up with the degrees that we're working with, but we only talked about it with a function that was in standard form, right? We did not talk about that with a function in factored form. So let's consider here, if we were to expand this cubic function out. You could try it out if you'd like. It would get a little bit clunky, a little bit messy, and that's okay. But if we were to expand this into, so we distribute here, here we use our FOIL, and then we distribute once more because we have another factor that we would be distributing. We could go through that if we wanted to. But the short form, what we will notice is the number of x's that are involved. If we consider that at any point, if we were to expand this, we would end up with one term, just one of the terms, would be x times 4x, right? And that is, we would have one term that was x cubed. So if we count out in total the number of x's that are involved up here, again, in factored form here, if we count out all of the number of x's involved there, then we can determine the degree of the polynomial. In this case, there are 3 x's. That means we're working with a cubic function. Okay, so that's a little aside how we can determine the degree of a function if it's not in standard form. If you're confused by that, we can go over that a little bit more in class. Now, if a function has a single root, okay, so that's what we call it if the function has, if the factor has an exponent 1, like each of these here. Okay, so if a function has a single root, again, we can say it order 1, at x equals b. Okay, so let's say there's a certain point where it has a root that has an exponent 1. It has a factor with an exponent 1. Okay, then the function, we would say it passes through the x-axis at x equals b. And that makes sense. This is just a fancy way of saying, like up here, our quadratic function passed through the x-axis at each of these points, right? At each of these roots. It passes through. If we zoom in to the function right at each of these axes, and it actually won't let me zoom in too much more. If we completely zoom in right here, it would actually look, if I draw it a little bit bigger, there's R, it would actually look almost linear just near the x-axis, right? It's almost linear. It looks like it's a little steeper than that, something like this. It looks almost linear, and that's the point. It's just crossing through the x-axis. Again, if that seems a little wonky, that's okay. We will get used to it. Okay, so if a function has a single root at x equals b, then the function passes through, like I demonstrated above, the x-axis at x equals b. Again, just like that quadratic we handled initially. Now, we'll consider after, are there any other ways for a function to have roots? Are there any other ways for a function to touch the x-axis? Well, right here, we're just focused on the first one. So a function behaves linearly near x equals b. So that means if we have a function right here, I know it says ... that's not involved in the function. We're just going to draw some conclusions to this function. So let's say we have this function right here. F at x equals a times x plus 2 times x minus 3. What that means that we're working with here, we should remember from yesterday, out from a, we can determine our end behaviors. And we can determine And basically that is a vertical stretch or a vertical compression factor. Okay, now from x plus 2, that tells me that there's a single root, again single because there's an exponent 1 here, a single root. And where is this single root? It's at x equals, and I'll give you a moment to think about it, x equals negative 2. Okay, now where x minus 3 is a factor, again with a hidden exponent 1, so it means there's another single root. This time it's at x equals positive 3. Okay, now if they're single roots, it means that the function behaves linearly near x equals b. So if there's a single root, let's see, that was at x equals 3. So right here, and then there was a single root as well at x equals minus 2. So we'll work with that right here. And our a value, we're actually not told. So this is that's a family of functions, right, because of this a value here. So this family of functions, it will have these singular roots. So let's say a was a positive value, then it would open up. We would be looking at a quadratic, something like this. Again, this is if a is greater than 0. Or if we wanted to, we could consider a function where a is less than 0, in which case it opens down. We're looking at something like this, if a is less than 0. Either way, here we're working with a quadratic function, but the point we wanted to consider was if we zoom in to any of these roots, we notice that our function is crossing the x-axis at those roots. That's what we're focused on right now. Okay, now are there any other ways for a function to have roots? Well, if we consider any quadratic function, right, like this here, looks like it's in 2 lines. Let's try that again. If we consider this quadratic function right here, if I were to move it around, if I were to translate it up, all of a sudden, okay, well there, the way this quadratic function is interacting with my x-axis, it's just touching, it's not crossing. In which case it's behaving, I'll put it back where it belongs. There it is, nice and happy. In which case it could be behaving like a quadratic function, like a parabola near the axis. And we'll be looking at that. So if a function has a double root, and that is order 2 at x equals b, then the function has a turning point at x equals b. Okay, so again, where it's behaving like a parabola. This function will behave parabolically in shape at x equals b. Its factor will be of the form x minus b squared. Again, it's this squared. That's what makes it order 2. Okay, so this function, let's look at it here, where f at x equals a times x, x minus 2 times x minus 3. This means that we have 2 roots involved, right? One of the roots that we're working with is a single root, again, because there's a hidden exponent 1, so it's a single root at x equals positive 2. And the next one we would have, and you know what, I'm just going to change this up a little bit to give us more space with our work here. So we'll say here it has a double root, because, and we notice that from the exponent 2, that means it's an order 2, so it has a double root at x equals negative 3. Okay, so x equals negative 3, that's right here. X equals positive 2, that's up here. And what we're working with here is a function that has a double root. That means it's behaving parabolically in shape. So it might be behaving like this, where it's touching but not crossing the axis, or it could be behaving like this, where it's touching and not crossing the axis. We'll choose the first one right now. So it's behaving just around the axis like that. Then our function might do something like this and come down right through this, have a single root over here where it crosses the axis. Okay, so we see a single root here where it's crossing. Single root. Again, we're talking about the behavior of the function at the root. Okay, whereas the other one is clearly a double root because it's behaving. If we zoomed in all the way right here, then we would see it kind of looks, if you were to only see this part, you might guess that our function is quadratic in nature, right? And it's not really, the function's not a quadratic, this one's a cubic, but Either way, the function is behaving like a quadratic right here near the root. That's what we're focused on. Now, we have seen here two different ways a function can behave around a root. There is a third one here, and we did just learn about inflection points in the last video, so you might be feeling a little bit uncomfortable with them, and that's okay. But if we consider, say, our base cubic function, right, just y equals x cubed. This one here, something like this, is its shape. It has a point of inflection right here, where it changes from being concave down to concave up. Right? And if it changes there, then again, the point of inflection is right here in the middle. This point of inflection happens to be right on the axis, right where the root is. So we would call this a triple root, right? You notice right there, that's a triple root. Okay, so here, and we will we'll actually move it around a little bit more. I might actually put that graphic up again afterwards. I think that might be helpful in how we're visualizing it. But either way, so we say it has a triple root at x equals b, again, order 3, then the function will have an inflection point at x equals b. That means it behaves like a cubic. And again, like a cubic function, that basically, you might consider that to be a function that looks like it's sitting on the axis, right? It's sitting down nice and easily. It's touching, it's going from concave up over here to concave down there. So its factor would be of the form x minus b cubed. Again, it's this cubed that makes it order 3. And so this function, let's take a look here. So we have a times x minus 1. And again, x minus 1, that's a single root, right? Because there's a hidden 1 there. So this is a single root. At x equals 1. And our triple root that's going on here, that's a triple. And we know it's a triple root because there's an exponent of 3 here. It's a triple root at here x minus 2. X equals, sorry, negative 2. Okay, so let's erase the our work that we put in at first. A triple root at x equals negative 2. A single root at x equals positive 1. Right here. And we're working with, okay, so there's a single root right here. That's what we care about. And we can kind of draw that in first, right? So let's make it in this direction. That means that our function is above the axis over here, right? It's above the axis over here. Now, if it is, we need to act like a triple root here. Our function needs to sit on the axis right there. So our function might come up, come down, and sit on the axis here, where it does cross through the axis, but it does not cross straight through the axis. It comes parallel, actually, with the axis right in there, right very close. So we're very focused on what the function looks like as it's crossing the axis. Again, it's behaving linearly over here with a root of order 1, and it's behaving cubically. It's behaving like a cubic function over here with order 2. Sorry, order 3. Now, what I would like to point out just a little bit here before we move on. So that means, and I just kind of thought up this graphic as I was going over that last one. So you did take a look and see how a cubic function looks. Now let's actually just plot here. We'll plot 3 functions that you're very, very, very used to, and that is the first one is going to be our linear function. Just your base linear function, y equals x, looks just like this, right? So if I label this here, that is y equals x. And if we zoom in right here, this is how a single root will behave as it crosses the axis. It just goes right through the axis. It does not turn. It does not do anything else. It crosses straight through the axis. So it behaves like a linear function that's going on there. But then if we take a look at our base quadratic function, y equals x squared, again, it's a function that you have studied a lot. Please forgive the, let's try and fix that a little bit, the weird symmetry there. Something like this. Okay, so this quadratic function, again, it behaves like a parabola. Well, it is a parabola the whole way. That is y equals x squared. This is what a double root looks like right at the axis. And lastly, just as you saw the cubic function, I drew that one already, something like this here. A cubic function, y equals x cubed. That's how a root will behave right here at the axis. That's how, sorry, a triple root will behave right at the axis. Now we can kind of put that together, right? And maybe just pause here. If you're feeling a little overwhelmed right now, just pause, take a little bit of a break, come back to the video when you're feeling up for it, because we're about to take the lessons that we handled from those first few new pieces of information, and we're about to really mix them, combine them with the skills that we worked on from section 3.2. So I'm hoping now, if you're back, that you are feeling nice and ready to try and absorb, try and put it together here. So we can graph a polynomial function from factored form using the skills, again, that we have recently learned. So we already know from section 3.2, and again, I'll put that in brackets here. So if you're uncomfortable with this first step, I want you to practice 3.2 a little bit more. We know from 3.2, we can use the degree and the sign of A, and that is our stretch or compression factor, to determine the end behaviors of the function, right? So let's say here we're working with a function, and it is a little new to you today. It is new to you today to come up with the degree of a function in factored form. Again, if you want, you can expand it out. It would probably be good practice for you to expand a few of them out just to see how that goes. But we're just going to look at this function, and right here we can count the exponents on the variables, right? So I have one variable here and one variable here. The second variable has an exponent 2. The first variable has a hidden exponent 1. It's not right beside the variable, but it's involved with the variable, right? It's on the brackets that contain the variable. So in total here, our exponents, and rather our degree of our function is equal to 1 plus 2, and that equals 3. Okay, so when it's in factored form, we add up the exponents there. So this is of degree 3, and our A value is 2. So A equals 2, and 2 we know is greater than 0. Okay, so that should be able to tell us what's going on. Because our degree is 3, then our degree is odd. If our degree is odd, our end behaviors, our function behaves oppositely, right? It goes off towards positive infinity in one direction and negative infinity in the other direction, or vice versa right here. But either way, it does not have the same end behaviors. Now, because our A value here is positive and our function is odd, that means our end behaviors, and I'll pause here for you to try and think of the implication there. That means our end behaviors should be going as x approaches positive infinity, y should approach positive infinity. As x approaches negative infinity, y should approach negative infinity down here. These are the kinds of end behaviors. So you know what? I'm just going to give it a small arrow just right in the corner, just so I know the end behaviors, how our function will act. Okay, now, whoops. Let's get back here. There we are. Number 2. Okay, so now we want to use the skills that we just learned today. We want to use the location and the type of roots to determine the graph's behaviors at the x-axis, and that is how our graph behaves. I'm sorry for the weird zooming, folks, there. Let's try and fix that. That is, this will tell us how our graph behaves right at its roots. Well, where are the roots that we're working with here? I see 2 roots. I see a root, and here I'll give it a 2 because this is step 2 we're working on. I see 2 roots. I see a single root, and that is it has order 1 at x equals 3. So single root at x equals 3. Awesome. Then I see a double root, again, because the exponent is 2. So this is a double root. Double root at x equals 5. Okay, so let's put those in here. At x equals 3. Oops, sorry, folks. That should be at x equals negative 3. We all make mistakes in here. Hoping you yelled at your computer a little bit there. You yelled at Mr. Pasatka through the computer and you said, Mr. Pasatka, the single root is not at x equals 3, it's at x equals negative 3. But either way, we know where our roots are here, right? So we have a double root here, we have a single root here. So that means that our function, it has to come from this end behavior, right? We're focused on that. It has to come from this end behavior. It has a double root at x equals 5. So that means our function could come down like this and it has to have a turning point there because it's a double root. And then we know that there's a single root over here. So that means our function, again, it must come from over here. Our single root is there, so we cross right through the axis. Now, we're not quite sure how our function behaves in here, other than we know there's not another root, because if there were another root, then there would be another factor, and there's no other factor up here, right? So there's no other root, so that means the behavior of my function, it might be doing something wonky up here, who knows? But either way, and really it's not. We know the number of turning points that's our limit, but we're not positive what the graph is doing right here. So let's take a look at step number 3. Step number 3, we determine the y-intercept of the function to determine where our function crosses the y-axis. Now, if you're sitting here and you might think, okay, I don't really know how to find the y-intercept of a function. We haven't gone over that this chapter. You're right, we have not. But when you did go over that was from grade 9. And then what you did after grade 9, you went to grade 10 and you used this skill again. And then you went to grade 11 and you used this skill again. So you should be really comfortable with it. And either way, if you don't remember, it should come back to you very quickly. If you are finding the y-intercept of your function, then you're saying, okay, that means y equals, that means x equals 0. So we can set x equal to 0. And that is, it looks like this. That is f at 0 equals 2 times 0 plus 3 times 0 minus 5 squared. And that is, it equals, we can start simplifying it. That's 2 times 3 times negative 5 squared. Again, we're respecting bedmass here because we are respectful people. That's 2 times 3 times negative 5 squared. That's 25. And that is 6 times 25, 150. So our y-intercept is at 150. So let's call it right there, 150. So we know that our function must pass through there. So you might say, okay, well then our function looks like this. It has I know it has to touch here, it has to touch there, so it has a maximum at the axis here at y equals 150. Now, it does not actually have to. Okay, now this is very possible. It could be a function that looks like this, but it does not need to have a maximum there. It could go like this and have a maximum elsewhere. It does not necessarily have a maximum right there. Okay, so just kind of keep that in mind. But either way, we're piecing it together. We notice I'm hoping you were at least able to follow some steps involved here, because this is a skill that is well beyond your grade 11 skills. But it is something that you should be relatively comfortable with, maybe a little uncomfortable, but you should be able to follow, and before too long you should be able to do it on your own, handling a polynomial like this. Notice from that equation we went to a very nice sketch in here. So we'll keep right on going. Again, I know this is a bit of a long lesson. Don't feel bad if you have to pause, stand up, move around as you go through it, but please make sure you're doing your best to follow along as we're working here. So we're going to, I will emphasize a little bit, on an assessment, you will, without a doubt, you will get a problem that looks something like this, where you're going to have to use your skills to determine from an equation to determine the shape of a possible graph. Now, that means if I were to grade something like this, and obviously if you're just using this video for review, then you can skip right on forward. But if I'm grading something like this, you earn maybe 2 marks for the actual sketch. You earn most of your marks from setting up your explanation, right? So you need to make sure that you are setting up absolutely without a doubt, every single time. You must make sure you're arguing, first of all, what you know. So we know from here our end behaviors, and you know what? I did not do a very good job at that because I was busy talking out loud, but we know that tells us as x approaches negative infinity, y approaches negative infinity, and we know that as x approaches positive infinity, y approaches positive infinity. So ideally we have those written out, so you caught Mr. Pasatka not showing all of his work there. But what we were looking at, we should have written out what we determine. So we determine our end behaviors, we determine the single root and double root, and we determine our x-intercept, right? And here our y-intercept here. So we need to be careful. When we're setting this up, we're explicitly saying, using our function notation, because we're in grade 12, what are we doing? We're evaluating here f at 0, and then we're going through. So we also need to show our argument for it. Okay, we need to show how we know, because we're showing off our skills on an assessment. So we need to say, okay, well, I know that the degree equals 3. I know that's an odd number. I know that my a value is greater than 0. Because of those, that's how I know my n behaviors. Okay, my single root and double root, I know right from here. Right, with this, I think it shows your skills enough to be able to write them out rather than just sketching them right here. And lastly, you know your y-intercept because you calculated it all on your own. You did that work. That's how we know it. You need to make sure you're showing that this is where you earn the majority of your marks. Okay, that's a new skill that you really start to focus on in this course more so than you have before. Now let's try, actually what I encourage you to do is try using those new skills, try following those 3 steps. Number 1, where you use the degree and sine of a to find the n behaviors. Number 2, where you use the location and the types of roots to determine the behaviors at the x-axis. And number 3, you use the y-intercept to determine where the graph crosses the y-axis. I want you to use each of those 3 steps to try and come up with a possible graph for this function right here. And then even further, oh boy, you should be ready to handle a function like this. You should be able to handle a function like this. You'll be able to try them all out on your own. And this one's kind of fun. This might give you a little bit of a challenge. Try it out. You should be able to handle those. Okay. Now pushing forward, there is still a little bit more to go over here. So remember, and this is terminology that we went through already. A family of functions is what we call a set of equations with the same roots to the same degrees. Right? We went over that just 2 pages up. Right here. Even further, bear with me. This is good content, just scrolling through the note, right? A family of functions, we went through it right here. A family of functions has the same factors to the same exponents. Perfect. So, a family of functions, again, we see it right down here. It's a set of equations with the same roots to the same degrees. Now, so I want you to try and find the family of functions, the family of polynomials with these zeros. And that is, I'm not just looking for you to determine, I'm not just looking for you to say, okay, well then, let's see here. If we have a 0 at x equals 3, that means there's a factor x minus 3, right? If there's a 0 at x equals negative 2, that means there's a factor of 2x plus 1. If there's a factor at 0, it means there's a factor, if there's a root at 0, it means there's a factor of x. So what I'm not looking for you to do is just to say, okay, well then that means that our polynomial is y equals x minus 3, 2x plus 1 times x. It's a good try. You would miss out on some marks here, because what we need to show here, we need to show that we understand a family of functions is not just one function. A family of functions is all of the functions that match this criteria. So if we want to list all of the functions, we need a variable in there. We'll call it our stretch factor. Any stretch factor here at all will be a part of this family of functions. Okay, where it's assumed the limit on a is a must be an element of the real numbers, right? Now, a single root, and again, that really goes without saying because in this course we're only working with the real numbers. Now, let's keep going forward a little bit. So a single root, let's consider a different family. So and you know what? I will allow you. Yeah, I'll do one more with you right in here. So it has a single root at x equals 4. Okay, so that means x minus 4 is a factor. And it has a double root, so we need to be careful there. We must not forget double roots. Okay, so at x equals negative 2, so that means x plus 2 is a factor. And since it's a double root, it has an exponent of 2. Right over here, there's another double root at x equals 6. So that means we're working with x minus 6 rather. X minus 6 squared, because it's a double root. So that means the family of functions is, and let's go again, our family of functions is not y equals x minus 4 x plus 2 squared x minus 6. It's not just that, oops, squared. Our family of functions, we must remember to put in this a value right here. And rather, I'll emphasize as well these squares. We cannot forget those. Fantastic. So you should be able to handle something like that. What I will give you, I can see here we have example 7. I'm going to give that to you as a challenge problem. Yeah, I'll give that to you as a challenge problem. Try it out. You should be able to first find the family and then use some information. So first you can find the family of functions, then you can use some information here to determine the a value. So try that out. You should be able to handle that on your own. And then we're going to go through 8, I'll call them A and B. We're going to go through 8A together. 8B will be yours for practice work. So we want to try and find the equation. I want to try and find the equation from this graph. You'll notice we're going to use the same skills. The difference is in the past we went from an equation to a graph. Now we're going to go in the opposite direction from a graph to an equation. So what we know, we can start off with our roots. What do we have here? We have a root here. At x equals -4, we have a root. And what kind of a root? There is a double root, so we need to be careful there. Double root. Okay, at x equals 0, there's a single root. It behaves linearly. So at x equals 0, single root. And at x equals 4, again, a single root. So from there, we can come up with the family of functions. Okay, so the family of functions that we have, that is f at x equals a times x plus 4 squared, right, because it's a double root right there, times x, where x equals 0, so that factor is just x, and lastly a single root at x equals 4, so that's x minus 4. Awesome stuff. Now we can rearrange this. It is always a good habit to put our x value first, just so it doesn't get lost within the rotation of things. So let's just rearrange that here. That is ax times x plus 4 squared times x minus 4. We could get a little more into the conventions here, but we're not going to be that picky. Not in this course, not right now. Good. Now that we know our family of functions, and it's written nice and crisply, nice and cleanly for us, what we need to find is our a value. So in order to find a, what we need to do is use some of the information that we know. Well, what do we, oh my goodness, there we go. What do we know about our function? We know it goes through some points, right? We know it goes through this root, and it goes through that root, and it goes through that root. The problem is, roots are not going to be very helpful to us. If you think they will, try it out with a root. But the truth of the fact of the matter is, they're not going to be that helpful to us. What we're looking for on this graph is it to go cleanly through a point. So a point that we can find, you might see the point down here, -2, -2. You might see the point up here, 2, 6. Either way, what we're looking for, you might see 3.5, 4. We're looking for a single point. I'm going to use the point here, 2, 6. Okay, so we can substitute in. You can use any of those points. We can substitute in 2, 6 into f at x. And again, right here we're narrating our solution. That's very helpful to creating a solution that others can follow. So we sub 2, 6 into f at x. So that means we're looking for where 6 equals a times 2 times 2 plus 4 squared times 2 minus 4. And what we're doing is we want to isolate for a. That's our goal. If we can find a, then we can use that with the family of functions to write out the exact equation, which is what we're trying to do. So here, you should be able to handle something like this. That is 6 equals a times 2 times 2 plus 4 squared. So that's 6 squared times 2 minus 4. So that's -2. And that is... You can simplify this how you would like. I'm going to have a little bit of fun here. I'm going to cancel those out, leaving me with a 1 here, a times 2 times 6 times -2. And that is 1 divided by 2 times -2 times 6. So that's -4 times 6. So that's -24 equals a. If you should be able to handle a simplification like that on your own, even if you went about it using a little bit of a different strategy than I did there, right? You absolutely should be able to handle something like that. So what we're working with here, that means, and I just have enough space, that means f at x equals a, which I now know, and again, I'm just copying from here, a, whoops, what happened? Just copying from here, a, which equals 1 over negative 24. And if I want to clean that up even a little bit more, I put the negative sign in the numerator. So negative 1 over 24 times x plus 4 squared times x minus 4. That's the equation that I'm looking for. Okay, where all we were using, this is using a grade 9 skill over here. This is using one of the skills that we just picked up, using some of the new terminology. But altogether, it's not too long of a process in order to handle something like that. Just make sure, if you're doing this on an assessment, make sure you're narrating your solution, like the line right here. Make sure what you're doing, you are justifying. That's how you earn grades in this course. Okay, so you should now be able to handle everything from 3.3. If you made it all the way through, well done. That's a task unto itself. We might be looking at having some more longer videos like this one, but I'm hoping going into so much detail in those examples, I'm hoping it could help you out.